Radim Barta, and I'm going to be presenting Understanding the Brain, T1 and T2 of White Matter. This is going to be going into more detail in how we actually conduct NMR, nuclear magnetic resonance, at the UBC MRI Research Center, tying into what Alice Leon talked about, where she talked about more of the biology and how it's important for MS. I'm going to talk more about NMR. So first, basics of NMR. What does it actually mean to do nuclear magnetic resonance imaging? What they discovered is that if you take a sample that has nuclei in it and put it in a magnetic field, the nuclei will align with the magnetic field, and then if you disrupt this alignment through the use of a coil that creates a magnetic field in a perpendicular direction to the original magnetic field, you'll make the magnetization of the sample point in a different direction than the magnetic field through it. And what happens then is we get precession of the magnetic field of the sample around the magnetic field that it is in. Then the precession is related to the strength of the magnetic field by omega equals lambda b, which is b is the strength of the magnetic field, omega is the frequency of the precession, and gamma is the gyromagnetic ratio, which depends on the properties of the sample. So depending on the sample, and knowing the magnetic field, and knowing the precession, which we can measure with a coil using the law that magnetic field through the coil will cause a current through the coil, we can measure the frequency of the sample's of the precession, and using that in combination with the magnetic field that we know, we can find the gyromagnetic ratio and thereby determine what material is actually the sample is. So here's a GIF of what it actually looks like to put the sample in a magnetic field. In this depiction, the magnetic field is oriented along the z-axis, and the magnetic vector has initially been shifted so that it is pointing in the y direction. As you can see, it precesses around the magnetic field in the z direction, and it slowly recovers so that it is once again aligned. So the important thing about this kind of motion is that there's two kinds of decay or transformations happening. First of all, the magnetic vector is realigning with the z-axis, so there is a T1, which we call T1 recovery. It is how long it takes, or the time scale on which the magnetization vector returns to point along the direction of the magnetic field. And then the second decay, or time constant, is the decay of the size of the spiral. So that is the T2 decay. It is how quickly the transverse, in the transverse direction that the magnetization disappears. So these are so this is what we're actually seeing if you look at it, at only one particular thing. So the transverse relaxation is looking at the amplitude of the precession as a matter of time, and that's the T2 decay, or the spin-spin relaxation. And then when we were watching, we saw the magnetization return to the vertical as the T1 recovery, or spin lattice relaxation. So in white matter, the nerve cells are covered in myelin sheaths, and these myelin sheaths contain water. The water in these myelin sheaths has a shortened T2, and so we can tell the difference between myelin water and water from intra and extracellular water by measuring the T2. And I'll show you how we can conduct experiments to measure T2. The UBC MRI Research Center, as Alice Leon talked about, uses myelin water fraction, which is where after they have been able to distinguish myelin water from other water, they can take a ratio. And then this ratio is actually a direct measure of the amount of myelination going on in the brain, which is very important to the study of MS because it involves the demyelination of nerve cells. So what I'm going to talk about is the question that we had when we were conducting this research, because T2 is understood quite well in the brain. We understand there's two components, myelin and non-myelin. However, most of the time that research has been carried out, the T1 has been considered mono-exponential. However, recently there have been results that have shown that T1 might be more complicated, that there might be more components that we can distinguish. So what we wanted to do is look at a small sample and really get down to the understanding. So we wanted to answer what evidence is there for two T1s in brain, or especially in white matter specifically, and can multiple T1s really explain the data that this new research is seeing? And the reason we're seeing new research is not that it's being done badly before, it's just that as we improve our techniques and increase the strength of our magnetic fields, we can get more detail. So what was the experiment? We took a sample of bovine brain, so that's cow brain, and we put it in an NMR spectrometer, and we did two kinds of experiments. Inversion recovery followed by an FID sequence, and an inversion recovery followed by a CPMG sequence, and I will explain both of those. And we used two kinds of inversion pulses. A hard pulse, which was a really quick 180-degree pulse, and a soft pulse, a long 3-millisecond pulse. And I'll again explain why we're using inversion pulses. For what is important from this slide is the hard pulse is kind of what you think about if you're a theorist sitting down at your table and you say, okay, I'm going to imagine that I change the magnetization all the way 180 degrees. You imagine it happens instantly. That's what the hard pulse is trying to do. The soft pulse is what happens in medical MRI, where we don't want to expose the patient to rapidly changing magnetic fields, so it happens over a period of time, over 3 milliseconds. And this is a cow. So why do we do inversion recovery? What was that pulse I was talking about? The inversion recovery is how we can get at the T1 of the sample. We invert the magnetization all the way. In that GIF I showed you, the magnetization began in the XY plane. Here we're inverting it completely and watching it recover as it goes back up to natural. So it begins negative and relaxes back up to align with the magnetic field. What then followed was two different experiments. F3 induction decay, FID, and CPMG, which I'll talk about in just a second. FID is important to be used to understand T1. Essentially what you do is you just invert the magnetization, and as it recovers, you take measurements of what the magnetization is, and that gives you simply a T1 decay. The difficulty with free induction decay is that when you use an inversion pulse, you don't invert only water. So you get non-aqueous components as well. So this research is conducted by my colleague Saeed. He's working on his thesis right now for his PhD. And he took FID curves where the T1 was decaying, where the magnetization vector was inverted, and he was able to separate out non-aqueous and aqueous components by fitting to a section of the distribution which is exponential, but on a short time scale can be assumed linear. So he fits straight lines to a short time component, which we assume is primarily due to aqueous. Non-aqueous components have a very short T1 from other experiments done, so they decay away by the 0.2 millisecond mark. And then now I'm going to move on to CPMG T2 analysis. And what the CPMG is looking at the T2. So this is good. This is going back to understanding how we actually get myelin water fraction and things like that. So how we can find out the T2 is we first take a magnetization vector, and we first did the inversion. Recovery experiment. So we flipped the magnetic field all the way 180 degrees. So unlike in this diagram where it starts at the top, aligned with the field, we interrupted the recovery at some point, and turned at 90 degrees so that the magnetization was not fully recovered. And then we carried out a CPMG, which is a spin echo experiment, where we would measure, well, we would let the magnetization decohere, as you see in this diagram. The decoherence happens because the magnetic field is not uniform, and as we know, frequency is related directly to magnetic field. But 180-degree pulses turn every single magnetization vector. So essentially what we do is we flip the magnetization from being a positive z direction to being negative z direction. So the decoherence is actually in the opposite direction. And so they actually realign, as you see in this, and form echoes. They first decohere, then they cohere and form an echo. And it is the decay of these echoes that is the T2 decay, or the transverse decay, that defines how we, or that defines the T2 of the sample. Now, these are the T2 curves we actually collected. Each T2 curve corresponds to different inversion time. Now, we use NNLS to analyze the T2 distributions. So what we do is using algebraic method, we can separate it into components. And then this gives us myelin and IE water. And then we were able to, look at these components and look at the amplitude of each of those components as a function of inversion time, and fit those with NNLS to get T1 distributions for each component. And what we found out is that myelin, right here, has a different T1 than intra-extracellular water. Just to finish up, Saeed is also working on a four-pole model, which is the idea that we're seeing that T1 is more complicated than just the mono-exponential, possibly more complicated than the bi-exponential. So he's working on a four-pole model, which assumes the water is in 4 different pools. It exchanges, so we allow water to permeate the membranes and things like that, and we can calculate T1s. And he actually found that he could fit both the hard pulse data and the soft pulse data very well, and get T1 times and exchange times that match. So this shows that the four-pole model can fit both sets of data, so it has strong evidence for it. I would like to thank everyone who collaborated with me on this research, Dr. Alex McKay and the entire UBC Research Center. Thank you.
So we have time for maybe 1 or 2 questions.
Minimize use phase encoding and frequency encoding to retrieve spatial data for every bit, every box. So how would it be possible to use your T2 splitting, the fact that you want to measure 2 T2s for the same voxel in an MRI scatter?
Okay, that's a good question. So exactly, because we split the voxels voxel-wise, each voxel has a slightly different frequency, so we can separate an image into voxels. And what we're actually looking at is the signal from a particular voxel and decomposing that further into 2 different exponentials. So essentially we're just saying the signal from a voxel doesn't necessarily have to be mono-exponential. It doesn't have to have it doesn't have to be e to the minus t. It can be e to the minus t plus e to the minus t over 2. And so that's what the 2 components come from. We're separating from a single voxel 1 decay. In this case, we were just using 1 sample, so it was just like 1 big voxel. Does that make sense?
Well, my question was a little bit more, how do you retrieve at the same time the spatial information and the T2 information for a single voxel?
So in this case, there wasn't separated. In general, maybe we can talk about it after. I can explain. It is sometimes tricky to get your head around it. There's actually 2 different kinds of encoding to get 3-dimensional, and it involves understanding your sample and understanding the magnetic fields you're inputting and understanding the gradients very well. So if you want to talk to me about it, I'm happy to